Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this lecture we're going to discuss Chapter 8, and that deals with wind and weather. If we look at the case in point of the Edmund Fitzgerald in Lake Superior in 1975, at the time it was one of the largest ore carriers in the Great Lakes at 729 feet. An intense low pressure system moved into the Great Lakes, and wind speeds were estimated to be about 58 miles per hour, gusting to 85 miles per hour. And wave heights were from 12 feet to 16 feet. Recent studies show that the structural deficiencies in poor ship conditions played a major role in the sinking of the ship. This case in point serves as a reminder that even the largest ships are vulnerable to wind and weather. So in this chapter, we'll discuss what forces control the speed and direction of the wind. Different weather systems bring different types of weather depending on the air circulation that characterizes each system. So for instance, when we had a low pressure system this past winter in Atlantic City, what we saw is that where the low pressure system spent most of its time depended on whether we got a lot of rain or a lot of snow. If the low pressure system was to the west of Atlantic City, here we had the circulation patterns were bringing in warm air from the south, and we got mostly rain. If the low pressure system was situated off the coast, towards the east of Atlantic City, we had cold air coming in from Canada and a lot of snow. We also know that wind is the local motion of air measured relative to the rotation of the Earth. And in this chapter we will investigate the various forces that either initiate or modify atmospheric circulation. First, each force will be examined separately. Then we'll combine them to show you how they drive atmospheric circulation. So when we talk of a force, it's a push or a pull that can cause an object at rest to move, or it can alter the movement of an object already in motion. Force is a vector as opposed to a scalar. A scalar is something like temperature that just has magnitude. A vector has both magnitude and a direction. So for instance, it's not important enough to just say what the magnitude of the force is, how hard you're pulling at something. It's also important to say in what direction you're pulling. It is useful to apply each force governing the wind to a parcel that is a unit mass, so a single kilogram of air. So don't forget, when we talk about a parcel, we're talking about a certain number of air molecules. So in this case, we'll talk about a unit mass. So that's the number of air molecules in a kilogram of air. Newton has 3 laws that he's famous for. His second one is that the force equals the mass times the acceleration. The acceleration is a change in velocity per time. Velocity is also a vector, And velocity is the speed plus the direction of travel. So if something's accelerating, its speed can change, or its direction can change, or its speed and direction can change. The main forces that act on the wind consist of air pressure gradient. So if we have a high pressure and a low pressure, air will move from the high pressure to the low pressure. We have centripetal force. This isn't exactly a force, it's rather a group of forces. It's any force that causes something to move in a circle. We also have the Coriolis effect. This isn't a force per se, but it can affect the direction of the motion of our air parcels. We also have friction and the gravitational force, or the weight. First, let's talk about the pressure gradient force. As I said, in general, all this force is that we have a high pressure and a low pressure. Air will move from the high pressure to the low pressure. When we talk about a gradient, we're talking about some change in a property over distance. So for example, we have the pressure in Atlantic City, and we have the pressure in Philadelphia, and they might be different. And the pressure gradient is how much this pressure changes divided by the distance between the two places. Air pressure gradients exist whenever air pressure varies from one place to another. A horizontal pressure gradient refers to air pressure changes along a constant altitude surface. So for example, we could look at how the pressure gradient changes at sea level or at the 500 millibar height. They can be determined on a weather map by isobars, and the closer the isobars are together, and isobars are lines of constant pressure, the higher the pressure gradient force is. Don't forget that by convention, isobars are drawn 4 millibars apart. A vertical air pressure gradient exists over a certain point, and it's a permanent feature of the atmosphere. So for example, we know that at the surface, the air pressure is about 1 times 10 to the 5th pascals, or newtons over meters squared. As we move up through the atmosphere, the air pressure decreases. So if you want an idea of how the pressure gradient force works, let's go ahead and look at a bathtub, and we'll push all the water to one side. So what we end up with is where the water height is large, we have a high pressure area. So here, we have the pressure at the bottom is equal to the weight of the column of water above it. So we have a high pressure here. Here, the height of the water is much lower, so we have a low pressure. And if I stop pushing the water to the high pressure and I let it go, what will happen? The water from the high pressure will move over to the water at the low pressure, and it'll try to even it out. So, in response to a pressure gradient, water or air, or any fluid, flows from an area of high pressure to an area of low pressure. We also have the centripetal force. Whenever you have something moving in a circle, there has to be a force towards the center of the circle. So I'm sure when you were a little kid, you probably took a string and tied a rock or something to that piece of string, and you swung it over your head, just like Goliath fighting the giant. If you think about it, the only way you could apply a force is in towards the center of the circle by pulling on the string. And what would happen is the rock or whatever you had tied to the string would move in a circle. I know there's a force towards the center because if I cut the string, the rock would move off in a straight line. It wouldn't continue to move in a circle. So if something's moving in a circle, there has to be a force towards the center, and this force we call the centripetal force. So if we look at a weather map, we have isobars are plotted on a surface weather map, and they're usually curved. And the wind blows in this curved path. The curved motion indicates the influence of the centripetal force. Now the centripetal force, once again, is just a category of forces. So for instance, it could be the pressure gradient force, or it could be weight, or it could be the tension in the string that you're applying with the rock tied to it. Whatever it is, it's towards the center. So the centripetal force is a center-seeking force. We actually can increase the rotation rate, the number of times it rotates per second, by shortening the string. So pulling in on the string. Once again, this requires a large centripetal force. A lot of times we'll see winds turning in a circle. This isn't exactly due to a force, but rather due to something we call the Coriolis effect. Think of it this way. If you had a plane that took off from the Atlantic City airport and headed straight towards the North Pole, if it continued its straight path, what would happen is that it would actually start to turn. The reason being is that it's not tied to the earth like a car would be, and as it's moving straight towards the pole, the earth is turning. So if we were looking up from the Atlantic City airport, standing on the ground, we would see the plane start to curve. Now this is not due to a force exactly, but something we call the Coriolis effect. So as the plane is flying straight towards the North Pole or the South Pole, it appears to be turning because we're standing on the earth and the earth is turning. So here we see the familiar north-south, east-west frame of reference, and it rotates in space as the earth rotates around its axis. If we look on the northern hemisphere, what happens is if we move towards the North Pole, we see that it's deflected. The air would be deflected to the right. If you're moving towards the South Pole in the northern hemisphere, what would happen is we would be headed towards the left. So if we head north, we turn to the right. If we head south, we turn to the left. This is in the northern hemisphere. If we combine these two, what we'd see is that we'd be moving in a clockwise direction. In the southern hemisphere, if we move towards the South Pole, we would move to the right. And if we move towards the equator, we would move to the left. And what we get is a counterclockwise flow. So the deflection is to the right in the northern hemisphere and to the left in the southern hemisphere. The deflection is strongest at the poles, and it decreases moving away from the poles, and it's actually zero at the equator. If fast-moving objects are deflected more than slow-moving objects, and the longer the trajectory, the greater the shift of the rotating coordinate system. So the more we move north or south, the greater the curve would be. The Coriolis effect only significantly influences winds in large-scale weather systems. We also have friction. You probably know what friction is. It's what causes things to slow down. So if we had something that was sliding across the road and it was moving at some velocity and we didn't keep pushing it, it would slow to a stop. And this is due to friction. We also see friction as the resistance of fluids, liquids and gases, to a flow, and it's termed viscosity. So there's two types. Molecular viscosity, that's the random motions of fluids, of molecules in the fluid, and eddy viscosity. This arises from a much larger irregular motion called eddies. The place that friction is important we call the atmospheric boundary level. So, if you've ever flown a kite, you've probably noticed that to get the kite up into the air, you probably had to run. You had to create your own wind. As it got higher up into the atmosphere, you didn't have to run anymore because the wind was blowing stronger or faster up at those high altitudes. Eventually, the influence of the friction along the ground dies off. So the place where this friction is important, we call the atmospheric boundary layer. We also have something called turbulence. This is fluid flow that's characterized by eddy motions. And we can see we experience turbulent eddies as gusts of wind. So here's some examples of eddy viscosity. If you watch a river that's flowing down a mountain stream, it'll hit a bunch of rocks and break up the motion. And what we'll get is little eddies that form around the rocks. Snow fences do the same thing. The snow fences are meant to tap some of the wind's kinetic energy, and they break up the wind into small eddies. And the wind speed diminishes, causing the loss of snow transporting ability. So for instance, if we wanted to keep snow off of a field or something, we'd put up a snow fence, and it would break up the wind and cause the snow to fall before it travels very far. Anytime you're near a large planet, you have gravitational forces. So gravity is the force that holds an object to the Earth's surface. It also keeps our atmosphere in place. If there was no gravity, our atmosphere would disperse out into space. We see that the net force of the gravitational and centripetal, that's the force towards the center, force, we see that gravitation is the force of attraction between the Earth and some object. So for example, the reason that the moon circles the Earth is because of gravity, and gravity gives you the centripetal force towards the center that causes the moon, to circle the Earth. Its magnitude is directly proportional to the product of the masses of the Earth and whatever object you're attracting. So for example, if it's the moon, it's the mass of the moon. If it's a baseball, it's the mass of the baseball. It's also inversely proportional to the square of the distance between the centers of mass. So the higher up you throw a baseball, the less gravity acts on it. We also have a much weaker centripetal force caused by the Earth's rotation. So gravity always acts downward towards the center of the Earth. It really doesn't influence horizontal winds, so the winds that are blowing parallel to the surface are not affected by gravity. It only influences air that's ascending or descending. And it always acts towards the center of the Earth, and the average acceleration near the Earth's surface is 9.8 meters per second per second. So what does this mean? It means if I take a baseball and I hold it up really high from the surface of the Earth and I let it go, each second it drops, you're going to add 9.8 meters per second to the velocity. So if I drop it from rest after the first second, it's moving 9.8 meters per second. After the second second, it's moving at 19.6 meters per second. So each second will add 9.8 meters per second to the velocity. So let's summarize our forces. We have horizontal pressure gradient. It's responsible for initiation of almost all air motion. If we have a high pressure and a low pressure, air will move from the high pressure to the low pressure. It accelerates air parcels perpendicular to isobars, and once again away from high pressure towards low pressure. We also have that centripetal force. This actually is a force towards the center, and it's a generic name for any force that points towards the center. There must be a centripetal force if there's a wind moving in a circle or a curved path. The centripetal force usually changes wind direction, not wind speed. And it always directed inward towards the center of the rotation. The Coriolis effect is not a force, but it appears to be a force, and the reason is if we have a wind that's blowing up north or down south, it'll appear to turn to the right in the northern hemisphere and to the left in the southern hemisphere, and the reason for this is that the Earth is spinning underneath it. We also have friction. Friction always acts to slow things down. It acts in the opposite direction of the wind direction. And it increases with increasing surface roughness. So for example, if we want to decrease the friction, we sand something. Make it nice and smooth so there won't be as much friction. Friction acts in the opposite direction of the wind direction. It increases with increasing surface roughness. And it slows horizontal winds with about 1,000 meters, or about 3,300 feet of the surface. So if the wind's blowing, it probably is blowing very slowly at the surface of the Earth, and as you move up through the atmosphere, it blows harder and harder and faster and faster. Our last force that we talked about was the gravitational force, and gravity accelerates air downward. So if the air is moving up, it slows it down. If the air is moving up, if the air is moving down, gravity will make it move faster and faster in a downward direction. It doesn't have any effect on the horizontal winds. So if we have a wind that's blowing from Atlantic City to Philadelphia, it won't affect that wind because it only acts down. Newton's first law of motion states that if an object is at rest, it'll remain at rest unless there's a non-zero net force. By net force, we mean sum of the forces. So for example, if you're moving a dresser or a piece of furniture, and one person's on one side pushing east at 100 newtons, and somebody's on the other side pushing 100 newtons to the west, the object won't move. If both those people got on the same side and pushed the dresser to the east, then it would move to the east. Also, he said that if an object is moving at a constant velocity, and that means a constant speed in a constant direction, the net forces also must be zero. So now we get the idea that we can add these forces up. So for instance, if you're moving a heavy piece of furniture, you can get you and two of your friends to push really hard, and the force that's exerted on that piece of furniture will be the sum of all three of you pushing. So what we're going to look at is the interaction of these forces, and they control vertical and horizontal airflow. And we're going to talk about the hydrostatic equilibrium, the geostrophic wind, the gradient wind, and surface winds. These are horizontal winds within the atmospheric boundary layer. Okay, here's a strange thing. I keep telling you that if there's a high pressure and a low pressure, air will move from the high pressure to the low pressure. I also told you that at the surface of the Earth, the pressure is quite large, and as we move up through the atmosphere, the pressure decreases. So the top of the atmosphere must be low pressure. So why doesn't all the air move up? Why don't we have strong wind blowing up through the atmosphere from the high pressure to the low pressure? And the reason for this is because we have something called the hydrostatic equilibrium. This vertical pressure up, due to the pressure gradient force, is balanced by the weight of the parcel down. So what we normally see is that the velocity of the wind up or down is usually quite small. And normally what happens is this hydrostatic equilibrium cancels out the forces and it doesn't accelerate very much. Here's another strange thing. If you look at things like hurricanes, what you'll see is that there's a low and air is blowing around the low, and that's where we get our hurricane from. But once again, I told you that air moves from a high pressure to a low pressure. So why isn't the wind blowing straight in towards the low? And the reason is we have something called the geostrophic wind. And what will happen is as we move up into the atmosphere, the Coriolis effect will counterbalance the pressure gradient force, and what we'll see is that the wind will blow parallel to the isobars. So for example, here's a 612, here's a 616, here's a 608. If we didn't have the Coriolis effect, the wind would blow from the 616 towards the 608. But what happens is, as we move up through the atmosphere, we lose the effect of the frictional force with the surface of the Earth, and what happens is this pressure gradient force gets canceled out by the Coriolis effect, and the wind actually blows parallel. So the pressure gradient force is still there. It's just counteracted by the Coriolis effect. Once again, we call this the geostrophic wind, and we say at high altitudes, the wind actually blows parallel to the isobars, where the isobars are lines of constant pressure. So if we look at the gradient wind, if we look at a high, it moves in a constant and a clockwise direction in the northern hemisphere. And if we look at the lows, they blow in a counterclockwise direction in the northern hemisphere. When we have surface winds, we have to add in the Coriolis effect and the force of friction. So what we see is that here's a high pressure, here's a low pressure. The pressure gradient force pushes from high to low. The Coriolis effect in the northern hemisphere would push towards this direction. And we also have the frictional force, and it points in that direction. So we have to add those three forces together. That's the force of friction, the pressure gradient force, and the Coriolis effect. And that'll tell us the acceleration of the air parcels. As we move up through the atmosphere, this force of friction becomes less and less important. So what happens here is we add up all these forces and we see where the net force is. And here the net force is in this direction, so the force of friction becomes even less. And eventually the force of friction isn't there at all. So what we can see is that as we move up through the atmosphere, we can actually see wind blowing in different directions. So the wind will actually turn as we go up through the atmosphere. Sometimes you can even see clouds at different levels blowing in different directions. You'll see one cloud moving one way and another cloud closer to the Earth moving in another direction. So if we look at surface winds in the northern hemisphere, don't forget we still have friction there. So what we end up with is that if we have a high, wind blows out and it blows clockwise. If we have a low, wind blows in and blows counterclockwise. So for instance, if this low sits to the east of Atlantic City, what will happen is we have cold air blowing in from the south and warm air blowing cold air blowing down from the north and warm air blowing up from the south. So if this is located to the east of Atlantic City is going to have a cold day. If this is located to the west of Atlantic City, then Egg Harbor will have a cold day and Atlantic City will have a warm day. Once again, we have these isobars that are usually shown to be 4 millibars apart. And places where we have a lot of isobars in a small area, we have a large pressure gradient. Here, we have not many isobars in a small area, so we have a low pressure gradient force. So on a typical surface weather map, isobars exhibit clockwise curvatures around highs or ridges and counterclockwise curvatures around troughs or lows. We also have something called the continuity of the wind. So this shows how the horizontal and vertical components of the wind are linked. So if we have a high here, we said that air will blow out from the high. Well, if the air is blowing out on both sides, some air has to come down to fill in that vacuum. So what we see is that we get divergence on the surface and convergence up aloft. So this is shown by having a lot of wind blowing in and a little wind blowing out. What happened to the other air? It sank. We could also show this convergence as wind blowing in from both sides. But what normally happens is something that looks like this, where we have fast moving air on one side and less air on the other side because some of that air is sinking into this high. If we have a low, what happens? At the surface we have a convergence and then rising air, because the air all pushes together, it has to go somewhere, it goes up. And we have divergence, so we have a little bit of wind blowing in and a lot of wind blowing out. In a surface low, the horizontal winds converge towards the center. The air does not pile up at the center, but it ascends. So we have converging at the surface, diverging aloft. These cyclones are typically stormy weather systems with clouds and precipitation developing. Surface winds accelerate and undergo horizontal divergence when blowing from a rough surface to a smooth surface, so for instance from land to water. Surface winds undergo horizontal convergence when blowing from a smooth to a rough surface, so from water to land. So divergence of surface winds causes air to descend, whereas convergence of surface winds causes air to ascend. So when we monitor the wind, not only the wind speed is important, but also the direction. So wind velocity is a vector quantity. It means it has both magnitude, speed, and direction. Wind is usually distinguished between its horizontal and vertical components, and it doesn't blow very fast up into the air. Horizontally, it blows much faster. So the magnitude of the vertical motion is typically 1 to 10% of the horizontal wind speed. The most common instruments only measure the horizontal wind. So a weather vane consists of a free rotating and weighted arrow that points into the wind. The wind direction is the direction it's coming from, not blowing to. So don't forget, a north wind comes from the north. A south wind comes from the south. Sometimes we just want to know roughly what the wind looks like, and we use a windsock, and it stretches downwind. For wind speed, it can be estimated by using its effect on water using the Beaufort scale. So table 8.3 shows you the Beaufort scale. So for instance, the Beaufort number is 0, means it's calm, and it means if you saw any smoke, it would rise vertically. And the largest number is a 12, that's a hurricane, Here we have wind speeds of 119 kilometers per hour and larger, and it's very rare, it's disastrous, and we have much foam and spray, greatly reduced visibility. For measuring the wind, we use a cup anemometer, and this tells you what the speed is because what it does is watch the cups rotating, and from there we can get the speed. Another type of anemometer is a hot wire, and what happens is we heat the wire and we watch how much it cools off due to the wind speed. Aerovanes measure both wind speed and direction. And here we see 3 or 4 propellers spin at a rate proportional to the wind speed, and the back fin turns into the direction of the wind. We also have sonic anemometers, and these consist of 3 arms that send out ultrasonic pulses. So these are sound waves that are higher than human hearing. That's why they're ultrasonic. And the sound waves travel times are translated into wind speed direction. It should be noted that the instrument should be mounted 10 meters or 33 feet above the ground. And you don't really want to put it on the rooftop because what will happen is the wind will blow up and over the house and you won't get an accurate reading. We also have radiosondes, satellites, and wind profiles that measure the winds aloft. So here it shows 3 pictures: the cup anemometer, the aerovane, and the sonic anemometer. If we look at the scale of wind systems, we have the planetary scale. These are on the order of weeks to months, and they travel 10,000 to 40,000 kilometers. The synoptic scale is what we measure our weather by. That's 100 to 10,000 kilometers, right? So that'll be 60 miles to 6,000 miles. Next comes the mesoscale. That's 1 to 100 kilometers, and our time scale is hours to days. And the microscale is seconds to hours. So if you look at the planetary scale systems, they're large-scale wind belts encircling the planet. If we look at the synoptic scales, that's continental or oceanic in nature. So these are migrating cyclones, hurricanes, and air masses. The mesoscale systems are circulation systems that influence the weather in part of a city or a county. So we're talking about on the order of thunderstorms and sea breezes. Microscale weather covers a very small area such as city blocks, and this could be like a weak tornado. So in conclusion, we see that unequal rates of radial heating and cooling within the Earth's atmosphere systems are responsible for temperature gradients. And we see that the atmosphere circulates in response to these heat energy, which is converted into kinetic energy. And we have forces that we studied in this chapter shape the atmospheric flow or atmospheric circulation, which we call the wind. And this chapter built a realistic model of atmospheric motion that demonstrates why and how the wind circulates around highs and lows, which are pressure systems. All right, thank you for your time.